Okay, so I have to ask you to preview propositions 7.7.8 to 7.7.f in the supplemental notes. Okay, so I will state the main theorem of this section. All right, so let the moment generating function as we define to be the expectation of the exponential function of a random variable x. All right, so let this moment generating function be defined on a neighborhood D, all right, which is the open interval from -epsilon to epsilon of the origin in the real line. Okay, so suppose that after the computation that of this moment generating function, we find that this function is defined for every t in this open interval. Okay, and this is a neighborhood of the origin. Then we have first every nth moment okay, as defined to be the expectation of the nth power of x exists and is finite. Okay, so this is a very strong result. Okay, the second thing is that the moment generating function has a power series expansion at the origin in R associated with the formal power series f of z okay. So this is a formal power series. The coefficient of the nth term is the nth moment divided by n factorial. Okay, so this is formal power series. And the power series has the radius of convergence we call ROC, is no less than the epsilon here. Okay. All right, so as we discussed in the supplemental notes that for a formal pulse series, we can consider the radius of convergence. Okay. And this is, can be done by root test, okay, as we stated in a few propositions, which is just a review of the results you may have learned in calculus. Okay, but okay, and so that so when the formal pulse series has a non-empty radius of a non-zero radius of convergence, then we can define a function by pulse series. Okay, so that this turns to be. So as we know that. So in this case, because that the radius of convergence of this formal pulse series is no less than epsilon. So as we discussed in the supplemental notes, so this implies that if we define a function, okay, then this is right. So that so this is a series for converges for all x in this neighborhood of the origin. Okay, so maybe I will say, I'm sorry, so that it comes to here. Okay, so which implies that the moment-generating function is a pulse series expansion. Okay, and so a representation of this function would be like this one. And proof. All right, and also in the supplemental notes, I already give a detailed proof of this proposition. Okay, using using propositions 7.7.8 to 7.7.f. Okay. All right. Because the proof is a little bit it's a little bit long, so I omitted in the class lecture. All right, so I ask you, do you have any question about the statement of the proposition? Okay. So let me emphasize the point. The major point in this proposition is that if the moment-generating function of a random variable x is defined, which we can, when we compute this expectation for t, and we find that this expectation exists is finite, okay, for every t in this neighborhood. Okay, suppose we have this, then every nth moment of x exists is finite. Okay, so that is a very strong result, And the second thing is that the moment generating function itself has power series expansion. And the coefficients involving the nth moment. Okay, so the coefficients of the power series would be the nth moment divided by n factorial. Okay. So that from here, it gives us a very quick way to find the nth moment. Okay. And so this will be stated in the next proposition. So let the moment generating function of random variable x be defined on a neighborhood of the origin in R All right, so then x has every nth moment m sub n, and the moment generating function has nth derivative at the origin. Okay, it's ended on D for every n, such that the nth moment can be computed to be the nth derivative of the moment generating function evaluated at the origin. All right, now, so x has every nth moment is from the proposition 7.7.g, right? Because 7.7.g state that the existence of the nth moment. Okay, and the moment generating function has nth derivative is because that the second stemma here, it has a power series expansion, okay, and by the discussion, okay, in the supplemental notes, that if a formal power series has a non-zero radius of convergence, then its formal derivative also has the same radius of convergence. Okay, so that is the main point of the reason why we discuss formal power series. Okay, but essentially it is from the root test. All right, so if a formal power series has a non-zero radius of convergence, then its formal power series has the same radius convergence, and then the formal derivative of the formal derivative also has the same radius of convergence. Okay, so that you can see that they will have you can do the formal derivative in any order. Okay, so that and the proposition in the supplemental notes says that that the formal power series is formal derivative, okay? Because they have the same radius of convergence, so they define a function. And this function is actually the derivative of the function associated with the original formal power series. So that means that this moment generating function, because it has the a positive expansion, and for all t, for all t in the neighborhood of the origin, so that this function has any order, has nth order of derivative for any n. Okay, so you can do derivative, okay, for any order. All right, so the nth derivative of the moment generating function always exists, and from the theory of power series expansion, you know, as you learned from calculus, that all right, that this if you evaluate it at t equal to 0, because the expansion is at the origin, okay. So that so this here, the numerator here, actually x equal to the nth derivative of the moment generating function evaluated at t equal to 0. Okay, so that they have equality. Okay, so from this proposition, you can see that we can generate the moments if we have the moment generating function f of x, because it's quite easy that you just evaluate the nth derivative of the moment generating function and evaluate the nth derivative at t equal to 0. Okay. Yeah. So the proof is actually by propositions 7.7.d and 7.7.g there. Okay, so okay. Now we will see a few applications of moment generating functions. Before that, we list. So a list right? So give this is distribution. This is the moment generating function. Right, so the first one is the binomial distribution with parameters NP. Okay, so a binomial distribution has two parameters. One is n and the other is p. And so the moment general function becomes to be p of e to t plus 1 minus p and raised to the nth power. Okay. The second Poisson with parameter. A Poisson distribution has one parameter. Okay. Right, so the moment general function of a Poisson distribution with parameter lambda would be this one. Geometric with parameter p and that would be p e to the tth power 1 minus p times e to the tth power. All right, a negative binomial with parameters R and P. Okay, so that would be P of E times T divided by 1 minus P e to the T's power and raised to the R's power. Okay, so the first four are discrete is the distribution of discrete random variables. Okay. Right, and next we have a uniform. Okay. Over AB. So the would be e to the t times b minus e to the t times a divided by t v minus a here. An exponential with parameter lambda greater than or equal to 0. This lambda divided by lambda minus t here. Gamma distribution with parameters. So there are two parameters, alpha and lambda. Alpha and 0. Lambda is also positive. Raised to the hour's power. And the last one is normal distribution with parameters mu and sigma square. Okay. And then the moment general function of a normally distributed random variable would be e to the mu t plus sigma square divided by 2 t square. Okay. And so as we can see that so that the D, the defining interval, for the binomial distribution, as you can see that this moment-driven function defined for all t, okay, in R here, okay, and the same for the Poisson. So you can see for the Poisson distribution, it has this right? And for the geometric function, so you can see that because the denominator cannot be 0, okay? So you can see the t you can have, okay? So you see that. You can look at 1 minus p e to t. Okay, so which means that e to t is 1 here. So t is the logarithm of 3 here. All right, so D would be, you can say that it's the minus and okay, so you can see that, and it's usually we restrict p in between 0 and 1. Okay. So that 1 minus p always in between 0 and 1. And its inverse always greater than 1. Okay. So that this is always positive. This is always positive. Okay. And for the negative binomial, okay, as you can see, this one is also okay. The same with restrictive ourselves to be 1 here. And for the uniform distribution, okay, even though you see 0, t cannot be 0, but as you can see that because when t is 0, the numerator also is 0, right? So that it has a limiting value. And indeed, actually, when t is 0, this always exists. All right, so d is also the whole real line here. Okay, and for the exponential parameter distributions, the lambda, so you can see d is in between. Okay, and here. Okay, so you can see for every one, you see that you always you can find an epsilon which is positive. Okay, and so that this. Let me finish the list here. So again, for gamma distribution, you have this. And for the normal distribution, this is the whole real line. Okay, so for these 8 distributions, the moment generating functions, okay, is defined on a neighborhood of the origin. Okay, the origin. So from proposition 7.7.g, you know that each of the 8 distributions has nth moment for every n. Okay, so they will have the nth moment for every n. Okay. And because we know the moment generating function, so we can use this formula, right, in the proposition 7.7.h to find the nth moment. Okay, so we just take the derivative of the nth derivative of the moment generating function here. All right, and please see the derivation of the moment generating function in the list in the textbook. So the textbook gives the computation of these moment generating functions. Okay, so you have to read the textbook to know how we can derive this moment generating function for these 4 distributions. Any questions? Okay. Okay. Now we can apply this an illustration of the power of moment generating function is to provide an alternative proof of several results on the CDF of the sum of independent random variables of the same kind. All right, so that we address this illustration in a general setting. So let Z, okay, is the sum of 2 random variables. Be the sum of 2 independent random variables. X and Y. Then the moment generating function of Z, by definition, X okay, this ETZ, and because Z is X plus Y, so it's ETX times ETY. Okay. Now, since ETX and ETY are independent, random variables. Okay. Because they are functions. This is a function of X. This is a function of Y. Okay? And because X and Y are independent, so their functions are independent too. Okay? I think this is by proposition 6 point, let me see. This point 2 point J. Okay. So we have the expectation of the product of two independent random variables, and so this is become 2, the product of their expectations. Okay, and this is by proposition I think 7 point. Seven point 4.1. Okay. Okay, so that, and this is the moment generating function of X. The second factor is the moment generating function of Y. Okay. Okay, so I had to correct an error here. Okay, so if it's defined in D1 and is defined in D2. Then the moment generating function of their sum is defined in the D, which is minimum okay. So you take the minimum of E1 and E2. Okay. Any questions? And so by induction, if x1, x2 up to x sub n are independent random variables with moment generating function defined on D sub I okay. Then the sum has moment generating function m of z of t with is the product of the moment generating function of x sub I, right, which is defined on D minus the minimum of epsilon I so their sum also has a moment generating function, which is just the product of the moment generating function of each summand. Okay, and this moment generating function is defined on a neighborhood of the origin. Okay, right, and the epsilon would be the minimum of the epsilon I. Okay. Any questions? So in proposition 6.3.1, it says that so let x1, x2 up to xn be an independent gamma random variables with parameters power 1 lambda, power 2 lambda, up to power sub n lambda. Okay, so you can see this n-independent gamma distributed random variable has different alpha parameters maybe, but will have the same lambda parameters. Okay. Then the sum z, which is x1 plus x2 plus xn of xi's is also a gamma random variable with parameters okay, so it's alpha 1. The alpha parameter will be the sum of the alpha parameters, and the lambda parameter will be the same. Okay. And now if we use the things so we see that the moment generating function of each gamma random variable x sub I, as we know here from the lists, that would be lambda divided by lambda minus t of the alpha I. Okay, so we from here. Now it's defined minus lambda up to lambda here. So m of z of t as the product okay. All right, so you can see this is now, the factors here has the same base, but with different exponents. So you can see this come to be. Okay. And is defined on the same here. And now, by the one-to-one correspondence between distribution and the moment generating function, as we stated last Thursday, right? So the moment generating function takes the form here, okay? It's the form like this one. So by the one-to-one correspondence, okay, so by the one-to-one correspondence between distributions and the moment generating functions z x gamma, so G is a gamma random variable with parameters 1 plus alpha 2 plus up to plus alpha n, and with the same lambda. Okay, so we have done the proof. Okay, that the proof will be very short. Okay. Now we look at another proposition we studied in chapter 6. So if x1, x2 up to xn be n independent normal random variables with respective parameters mu I, sigma I square for I from 1 up to n. Okay. So this independent normal random variable may have different means, may have different variances. Okay. Then the sum z equal to x1 of xi's is also a normal random variable with parameters the mean would be the sum of the mean, and the variance would be the sum of the variance. Okay. And the proof would be quite simple. Since so because each x of I is a normal random variables with these two parameters, so their moment generating function would be, an exponential function would be e mu I t plus 1/2 sigma I square t square. Okay? It's defined on the whole real line here. Now, the moment generating function of x sub I, of the sum of x sub i's, becomes to be the product of the moment generating function of each x sub I. Okay. And so that, and the vector would be the exponential function. Okay. But the product of exponential function will become to the exponential function of the sum of the exponent. So this is become 2. Okay, is that? And so would be I plus okay, and it's defined also on the whole real line here. So again, by the one-to-one correspondence, between distributions and moment generating functions, z is a normal, all right? Because that when we look at the moment generating function, we find that it is of this type. Okay, so it's a normal random variables with parameters. Sub I. So the mean would be the sum of the means of x sub I. And the variance would be the sum of the variance of each x sub I. Okay. So and we also discuss independent Poisson random variables. So all right, so that maybe I'll stay here. So let Z be the sum of an independent Poisson random variables with parameters lambda 1, lambda up to lambda n, respectively. Okay. Then Z is a Poisson random variables with parameter lambda, which is equal to the sum of each lambda sub I. Okay, and you can look at the moment-generating function here. So the proof is similar. So that it is an exponential function of lambda et minus 1 here. Lambda sub I e to t minus 1. Okay, so MZT is the product all right, so it is okay, so again, by the one-to-one correspondence between distributions and the M moment generating functions. Z is a Poisson random variable with parameter. Okay. Okay, and now similar argument can be applied to the sum Z of an independent negative binomial random variables with parameters I parameters x sub I with parameters Ri and P. Okay, so the P parameter will be the same, but the R parameters can be different. So that Z is a negative binomial random variable with parameters R1 plus R2 plus up to Rn, but the same P. Okay. Any questions? Okay. So the argument would be similar, and so you have to use the one-to-one correspondence between distributions, all right, and their moment generating functions. Of course, in here we just confine ourselves to distributions with moment generating function, which is defined in a neighborhood of the origin. Okay. Okay, so let's take a break up to 2:40. Now we consider an example. Okay. Right. So we'll find the moment generating function of the sum of a random number of independent and identically disputed random variables. Okay, so we let x1, x2, etc. be a sequence of independent and identically distributed random, so this is called IID, random variables. We let n be a non-negative integer valued random variable that is independent of x sub i's. All right, and so the first purpose is to compute the moment generating function of a random sum of x sub i's. Okay, so that we have the random sum here. Okay, and to do that, we will conditioning on n equal to little n. So we have that the expectation of the exponential function of y, okay, given n equal to n. Okay, and we know that n is a discrete random variable with the value is non-negative integer value, so possible value will be 0, 1, 2, 3, 4, etc. Okay. All right, so that this is actually exponential function. Oh, I'm sorry. So that it would be t of 2 capital N of x sub I. Okay. Now, given that non-variable n is equal to little n, so this is become to be little n x sub I. Okay. now. So now we have little n, so x1, x2 up to xn. And now this one is a function of okay. It's a function of x1, x2 up to xn. So that's ET is independent of the capital N here. And because of the independence, so that we can apply proposition 7.5.c, the independence property of conditional expectation. So this is come to become to the unconditional expectation. And so this becomes to be, because they are independent, so the sum. So this is to come to the product. The nth power. So where is the moment generating function of x sub I? Okay. Because x sub I has the same distribution, so they should have the same moment generating function. Okay, so we denote it as m sub x of t. Any questions? Okay. Okay, and so the moment generating function of the random sum of the x sub I becomes to be. So you see that. So that, okay, let me see. So that so that this random variable, right, is a function of n, is actually the nth power, capital Nth power here. So this is implies that the moment generating function And so expectation of the mxt nth power. So it's this. All right, so if we know the distribution of capital N, then we can find this expectation. All right, and the mean of y is here. So we know this is the first derivative of the moment generating function. Of course, that we assume that the moment generating function of x sub I is defined in a neighborhood of 0. Okay, so that this random sum from here, we know that it always also exists in the same neighborhood of the origin. Okay, okay, because this one exists and is finite for all t in the neighborhood of the origin, so that this moment generating function also defined on the same neighborhood of the origin. Okay, so that we should take the derivative. Okay, but that but you see, this is the derivative of okay. So is this, all right, so you can see that this is the serial sum of the power of the moment generating function of x sub I weighted by its moment generating, its mass, probability mass function of the discrete random variable n here. Okay. And actually, because the series always converges, you know, they always converge absolutely. Okay, so that we can exchange the order of the summation and the derivative. All right, to evaluate that. Okay, and so that this, you can see, this is And indeed, you can see that by the way, I'm sorry. The derivative actually, another one is the m x prime t. Sorry, the chain rule. Okay, and p. Okay, the chain rule there. All right, so this is the evaluation. And so this is actually the expectation of the n and m x0 minus 1. Okay. Okay. But this is equal to 1. So this is actually equal to, this is 1 and this is the equal to expectation of x. Okay. So this is E and expectation of x. This is constant, this is n. So again, we have that the expectation of the random sum of IID random variable x sub I is equal to the expectation of the x sub I and the expectation of the random number n. Okay. So here we have say exchangeable, the order exchangeable in order. In the neighborhood of the origin. So basically, they are exchangeable. And okay, and the second moment. So we know the second moment. Okay, is we evaluate the second derivative of the modern general function of y at t equal to 0. And you can actually see this is actually plus n. Okay. Oh, okay. Maybe I do it step by step for you. So this is D. Right. Is to evaluate here. All right, because we already see the moment generating function of y is the expectation of the capital N's power of the moment generating function of x. Okay, so you can have that. And okay, so actually we can exchange the expectation the nth power okay. So first of all, exchange the derivative operators and the expectation operators. Okay. Because we know that this summation, this expectation is actually a serious sum. So you can, of course, you can go through this process, but I just do it in a concise way. Okay. So this is actually the expectation. And you treat the random variable n as just a constant here when we do the differentiation. So this is actually d of dt. So we do the first. Okay. So this is n and the mxt n minus 1 and the mx from t. First, yeah. First of all, and then you will do the derivative again here. Now, when we do it, because this is the differentiation of the product up to function of t, so you will, for the first one, you get n minus 2, and you have the square plus n mxt n minus 1, and for this one, m double prime x of t. And t equals 0 here. The expectation. Okay. Now, you can do the substitution t equal to 0 here. Okay. So this is expectation of n n minus 1, and mx 0 to the m minus 2 power, and m ground x 0 square plus n m 0 m minus 1, and mx to the ground 0 here. Okay. Right, and we know this is equal to 1. The inner part is the expectation of x. Okay. This is equal to 1, and this is equal to the second moment of x here. All right, so you get expectation of n minus 1. This is 1, right? And this is the expectation of the square of the expectation of x, plus for here it's n here, this one, so this is of the second moment. Okay, you get this one. Okay, and so that you have two sums. So the first you have n square minus all right, this is about the first term, and for the second terms. Okay, you get this one here. Okay, so the expectation of n here, and the factor, you get the expectation of square minus the square of the expectation plus the second moment of n, and the square of the expectation. Okay, so this is you okay, because this term, these two terms has the same factor there, and this is just the variance of x. So this is expectation of n, and this is the variance of x plus the second moment of n times the square of the expectation of x. All right, and so finally the variance of y, as we know, it is the second moment of y minus the square of the expectation of y. And so you can, because you know the mean is this product. Okay. Okay, and so you have the second moment, as we have find, is here plus okay minus the square here. All right, so that En variance of x plus, right, plus the variance of n times the square of the expectation of x. Okay. Right, so this is the way we find that the variance of the random sum of x of i's, okay, of ID random variable x of i's. Okay. So that this involving the exchange of the like here, the exchange of the derivative and expectation. Okay, and okay, so the justification, if you want to justify that, you have to express the expectation as the series sum here. All right, so that they are able to exchange is because that the series is serious, that they converges, all right, to a finite number for each t in a neighborhood of the origin. Okay, so that you can do the differentiation at t equal to 0 and to do the evaluation there. Okay, all right, and for here I exchanged them because that we can justify that the order of the differentiation and the expectation can be exchanged by using the same procedure here. Okay, all right. And so you have to justify why, but they are we are able to exchange the order of differentiation. But for the moment genuine function, because that as we see that we usually consider moment genuine function which is defined in the neighborhood of the origin. Okay, so that it's always legitimate to do the exchange of the order of differentiation and expectation. Okay, and when we do the differentiation, we treat the random variable, because this random variable is independent of t, right? So that we can regard it them as a constant, okay, and because it's independent of t, so that we do the derivative, and we know that the n are just integers, non-negative integers, so we can do it this way. Okay, right. If the so that this is by the rule, okay. So it is more intuitive if you express the expectation as a serious sum. Okay, then everything is more clear. Even though that the process is a little bit lengthy, but this approach, I will encourage you to do these approaches. Okay, this one is that actually, if you can do that, you have to justify each steps. All right, so it's not always true. All right, to exchange the differentiation is expectation. Okay, but for our case, that it's okay. It's correct to do that. Okay, so if you consider the expectation, express expectation as the summation, because now the random value will be expressed by what? By the possible value there. Okay, so it's much more clear than this way. Okay, even though this way give you a very concise computation. Okay. All right, so before we leave the classroom, so we define the moment genuine function. of a single random variable. But actually, we can define, okay, the joint moment generating function m of x1, x2, up to x sub n with parameter t1, t2, up to tn of n random variables x1, x2, up to xn is defined as here. As the expectation of the exponential function of t1 times x1, t2 times x2, etc., up to tn times xn. Okay, so it has n parameters, and each corresponding to one random variables we considered. Okay? All right, and so for real t1, t2, up to tn, such that the expectation exists and is finite. Okay. So the extension is very straightforward. All right, very straightforward. We give a parameter for each random variable, and because we consider the joint moment generating function of n random variables, so we have a moment generating function with n parameters there. N parameters, right? So you can see that this is called corresponding to the multidimensional Laplace transform. Okay, if we extend the Laplace transform here, it's multidimensional Laplace transform. Okay, so we'll continue the discussion on moment generating function Thursday.